Great. So welcome, everyone. We're very happy to have with us today David Sauzin from the Institute of Celestial Mechanics and Computation of the Ephemerides in Paris. And he will give a mini course on Resurgence Theory, Generalized Borel-Laplace Summation, Alien Calculus, and Applications. Over to you, David. Yeah, and just one quick announcement. Online participants, you can type your questions in the chat box or raise your hand and I'll unmute you in case you're not able to unmute yourself.
Chat box, so please tell me if there is any question. Also, can you hear me? It's okay? Well, thank you, Pranav, and thank you to ICTS, its director. I'm very glad to be here for my first time in India. I'm delighted to be here and to have this wonderful opportunity of talking about resurgent theory. So it's a mini course. I will try to be slow and you're welcome to ask questions. And to start with, it will be very soft. I would like to talk about the subject from a historical viewpoint to start with. So yes, resurgence theory. Let's start with the very recent history. How does it work? Like this? Yes. Very recent history. This is a search on Central Blatt Mathematics, you know, on the database for published articles. And I looked for, in the past 3 years, any published article containing in its title, resurgence or resurgent. On that occasion, I discovered that algebraists have a notion of resurgence number, which has nothing to do with my topic. So I had to eliminate those. But still, I had 29 documents, 3 documents published just in 2022, and 26 others in 2021, 2020. So you see, the field is very active, it seems. And here I have highlighted for you just a few of them. Kontsevich, Zeubelmann, because maybe in my last lecture there will be something related to that. The second one you see, Marcos Marinho, he was invited to give a talk here a few months ago. So that's, well, he's been working on resurgence for maybe 10 years now, quite intensively. Of course, that's more physics. I define myself as a mathematician, so I will try to emphasize the mathematical side. And Garoufalidis, I would say, and Kashayev are also mathematicians, and this is something about quantum dilogarithm. And Garoufalidis, you know, is very interested in topological quantum field theory. And then what next have we on the list? I mean, there is no point in reading everything, but I highlighted just a few. Yes, keywords. Exact WKB. Exact WKB, that's something I will not discuss it in detail, but it's important to know that there is a connection with resurgence. Yes, here you have in yellow, you have 2 things. Resurgent analysis of 3 manifold invariants, or here SU2 Chern-Simons partition functions on Brieskorn spheres. That's quite interesting. That's related with another talk I should give here at the end of next week in the seminar. Here again, you have Garoufalidis and Marinho, and that's also quantum knot invariant. So that's still topological quantum field theory, I suppose. And then you have many others. And that's just the past 3 years. Here you have again exact WKB analysis and quantization conditions. Yes, Unzal, Mithat Unzal has been very active. And then many people, I mean, I'm in touch with Ricardo Schiappa, with Gerald Dune. I mean, there are many physicists working with these ideas, but also mathematicians. And here, well, the 3 last are about mathematics. I mean, Fauvet, Menous, and Keva. Fauvet, Menous are close collaborators of mine. And I highlighted that because there will be one example related to quantum field in 0 dimension. I don't know exactly what it means, but you probably know better than me. And this is a paper of mine with Shingo Kamimoto and endless Riemann surfaces. Resurgence is about endless analytic continuation. So that will be something to be defined in this mini course. And convolution product, iterated convolutions, that's not the easiest part of the theory, but that's an important part of the theory. Oh, and also very mathematical, algebraic combinatorics. These people are combinatorists, Chapoton, Malvenuto, Thibon. Actually, we had a project together. CARMA is the acronym for a French grant we had on algebraic combinatorics, resurgence, molds, and application. Molds, it's related to resurgence, and maybe we touched a little bit about mold calculus. So these are just names of people, words, keywords. The term resurgence was coined by Jean Écalle. So this is Jean Écalle's webpage, official webpage. He's a CNRS researcher in Orsay University, very active. He coined the term resurgence more than 40 years ago. And as you saw, very recently it has become popular. There has been a resurgence of interest for resurgence. But he was doing dynamics, dynamical systems. He was a mathematician working with the problems of classifications of local analytic dynamical systems. The dynamical systems, vector fields, but I mean local, it means there is a fixed point, a singularity. So local analysis near a fixed point, or iterating a map, discrete dynamical system, but again with a fixed point. And what can you say about the local analysis, the local study? He was into that at that time very much. And this is how he came about this structure that he called resurgence. I'm not implying that nobody had worked on those questions, but for instance, I mean, you will see it's about asymptotics. And there is an influential book by Dingle in UK about in the 70s, which is kind of precursor of resurgence in a sense. But well, I will focus on the French side of the history, I must say. So, and particularly Écalle. So what did he, I mean, on his webpage, you can find many preprints. And for instance, you will find those. In the early 80s, I hope you can read it. I hope it's not too small. In the early 80s, he published 3 volumes, 3 preprints. Actually, they were never publication. They were never published as books, but they are influential. This is the foundation of resurgence theory. So 3 preprints in Orsay, Publications mathématiques d'Orsay, in 1981, 81, and you see applied to iteration, discrete dynamical systems. And you see the 3rd volume, it's 85 analytic classifications of local objects, local dynamical systems in the analytic frame, complex holomorphic framework. There is a box in the middle because at the same time, André VOROS, you may know him, he's a well-known French physicist and mathematician as well, I must say. He was working on the quartic oscillator, a problem in quantum mechanics. And he was into the complex WKB method, which became the exact WKB method. So he published that in 83. It's a long paper and very important. Of course, again, he was not alone doing exact WKB analysis, but I mean, here, this is the French side of the history. He was working on that, and he talked to Bernard Malgrange, because they were neighbors, and Malgrange is a well-known mathematician in France, and Malgrange told him, oh, that's fascinating. You must talk to Écalle. Écalle has just discovered something, unraveled something. So they talked together, and actually, in this paper in 83, VOROS mentions that he has a conjecture, and probably this has to do with resurgent functions, this new thing from Écalle. And Écalle in 85 quotes VOROS problem as a different source of resurgence. And Écalle immediately said, yes, you're right, your conjecture is true, this is resurgence. And so WKB resurgence was born, or quantum resurgence, which is very much related to the surge of interest for resurgence because of, yes, I mentioned exact WKB. I discussed with Pranav this Gayotto-Moore-Neitzke, very important paper less than 10 years ago. This has to do with WKB. So, and this is in the direction of algebraic geometry, I suppose. So you see, it's going in many directions. In this mini course, we will be quiet. We don't not too fast, and I will stick to things I know well, and I hope to convey the flavor of the beautiful mathematics that we have here. So yes, what did Écalle? He published these 3 volumes. So let's dive into this volume. This is the cover of the first volume. 247 pages. And then you have the second volume, 280 pages. And then you have the third volume, 585 pages. As you can see, it's written in French. And here is the beginning of the table of contents of the first volume. As you can see, it's before tech and LaTeX. I said it's in French, but actually in the first and the third volume, there are forewords in English. So let's have a look at what Écalle himself wrote in English. So let me read the beginning of this. Is in the beginning of the third volume. The vastness of the area covered in this book induced us to pay greater attention to the clarity of the exposition than to the completeness of the proofs, which are often sketchy, especially when they merely develop or modify earlier arguments. No wonder then if the present volume reads in places more like a digest of commented results than a regular mathematical treatise. So that's 1,000 pages, and you don't have all the details, all the proofs. You have to fill the gaps yourself, and you have to decipher French, of course. And it's a bit innocent because you see how beautifully he writes in English, and his later papers are all in English. But here, I mean, it's a digression, but that's quite interesting, I think, to say that in India. He had a regret. At the beginning, we undertook to tell how a baffling variety of local objects could be classified by means of a single equation, the size of a postage stamp. But try as we may, there was no short way to tell the story. Instead of a postage stamp, we ended up with an unwieldy, circumvoluted book running into the 600 typewritten pages. So he feels disappointed about it. And he wonders, he asks the question, could we avoid such problems with mathematical exposition, especially written mathematical exposition? So he has this idea, which I show you now, the need for mathematical mandalas. The solution to that problem exists and must be sought in the form of large mathematical posters, or mandalas, as we prefer to call them, which would present the gist of a theory in a graphic, compellingly attractive manner. And then you have this 4-page text. So I invite you to have a look. On his webpage, you can find all this. Let us press here very briefly our case for mathematical mandalas. So you have 4 pages about what they should look like. And of course, the word mandala was not chosen by accident. It's a little small. To designate the objects we have just described, there were 3 possible words to choose from: poster, map, mandala. Poster and map we dismissed as being insufficiently evocative. Mandala simply means circle in Sanskrit, but the word acquired a highly specific meaning, and well, probably in India, you know that better than me. Actually, Écalle has spent a lot of time in India, I know. He knows some Indian languages, Sanskrit and Hindi, etc. I mean, he interesting mind. And well, I think he knows what he's writing here. So, well, I find it fun to tell you that in India here. Yes, on this file, I can forward it to anybody who's interested. I have put more references. This is in English from Écalle himself. And this is a book we wrote with Claudine Michi. So Claudine wrote the first part of the book about monodromy problems, Riemann-Hilbert, and I wrote the part on resurgence. So it's a lecture note, so it's a textbook gathering results, I mean, from Écalle. But as you read from, he himself said that the gaps needed to be filled. So in my research papers, I had sometimes tried to give more details and complete proofs for some of these results. And this is the first textbook which could gather such results. And there is more to come. Yes, but this we will not discuss today or no next week. So that's the end of my slides. So what should I do? I should stop share. Okay. And now.
Do you plan to use the blackboard?
Yes, I would like to use the blackboard.
Yeah, you can go ahead. AV team, would it be possible to, so you don't need the projector anymore at all?
Not at all, yeah, no, not at all.
Would it be possible to move the projector away? Yeah, thank you.
So I go on here, nothing to do more technically? Okay. So what is a resurgent function? That will be the goal of my lectures of this mini course. What is a resurgent function? Is it large enough? Even for, no, yes? Even in the back? Wow, thank you. Good eyes.
Online participants, are you able to, if you're not able to read it, then say something in the chat box.
Yes, a resurgent function is an analytic function of one variable, of one complex variable, obtained by Borel-Laplace summation, Borel-Laplace summation from a resurgent series. So it's not yet a formal definition. It's rather what we are aiming at. So it's where we are heading toward. Resurgent functions, they come from resurgent series via Borel-Laplace. So Borel-Laplace, that will be the classical part of the mini course. Borel, that's 1890, I think, his book on the Borel transform. But we will define Borel-Laplace summation, and we will define then resurgent series. So series, I mean series of one indeterminate. So let's say T. So this is the standard notation for the space of all series. All series, so any C0, C1, etc. in C without any condition on the growth of the coefficients. And of course, inside them, you find the convergent series. So these are the convergent series. Those which have non-zero, a positive radius of convergence. So you probably know that. So a series like this, let me put a tilde. Most often, I use phi tilde for formal series. So that's the generic element. And I say it's convergent if, only if the radius of convergence is positive, which means that there exist constants so that the modulus of the nth coefficient is less than Cm to the n, in which case the radius of convergence is at least 1 over m. That's it. So resurgent series come in various flavors. There will be R simp, R omega simp. So, for instance, R simp is a subspace of R, R simp omega is a subspace of R omega, and all of them are subspaces of, yes, formal series. So we will define them by some appropriate condition on the growth of coefficient, but something subtler than simply the growth. And of course, it will be more general than this. I mean, we will have an inclusion. So let me take the first two. There will be such an inclusion. And today I will define this guy, R. But let me advertise something extraordinary. I find it extraordinary. So this is a preview of various spaces of resurgent series, and now a preview of alien calculus. Yes, you heard well, alien. I mean, Écalle is very creative. He coined many terms, and well, he could have called them, he could have called it foreign calculus, but he decided to choose alien. No relation that I know with the famous movies of that time. So alien calculus, well, it's a theorem, it's a fact that we will encounter. For every omega non-zero complex number, one can define a linear operator I mean, a C linear operator with these are C vector spaces, delta omega. So this one will be on R simp to itself. So it's an endomorphism. Well, for the linear structure, it's a C linear map from a vector space to itself, which is a derivation satisfying Leibniz rule. The derivative of a product is well, Leibniz rule. So we are very interested in the product, in the algebra structure. When you multiply series, so you know you can multiply series, and this is an extension of the pointwise multiplication of functions, because every convergent series determines a holomorphic germ at the origin, which determines a function in a small disk. So we are speaking here of honest functions. Here we have series, maybe non-convergent. So a priori, maybe they mean nothing, of course. The series we encounter in physics, in mathematics, usually have a deep meaning. But the point is that it's not so easy to extract the meaning when the series is not convergent. So you have to, and well, Borel-Laplace is one way. That's the story. So you have the product, pointwise product for germs, for functions, let's say. And here the so-called Cauchy product, discrete convolution. Yes?
Sorry if I'm anticipating you, but if I may just ask in advance, if we were to specialize this to the pointwise convergent, I mean to the CFT, the convergence series, this presumably, at least for some value of omega, it reduces to the ordinary derivative. And if no, it doesn't?
It vanishes, it annihilates. I mean, they satisfy Leibniz rule and they annihilate all convergent series. Oh. They measure divergence. Ah. They detect divergence. It's okay. Convergent, zero. Nothing happens. So let me write, convergent series are all contained in the kernel of delta omega. So delta omega vanishes. But your question is excellent because the ordinary derivative here, it exists. I mean, it exists everywhere. I mean, in all this chain, you have, so here we have this family, this huge family of derivation, one for each non-zero complex number here. But if you go at the top of the tower, you have here, well, do you know all the derivations of that vector space? So that's an exercise I was discussing with two colleagues here. What are the derivation of that space? You have a ring. Can you describe all the possible linear maps which satisfy Leibniz rule? So d over dt is one of them, no doubt. It's defined from polynomials. I mean, this is the completion of polynomials, and d over dt is the one. Or you can have the viewpoint of infinitesimal calculus, d over dt. And now it's a theorem that, of course, if you multiply by f, it's still a derivation where f is any. So, I mean, it's a fact. So let me, it's a note. All derivations of the big algebra are of the form f of t d over dt with f an arbitrary element. And for the same price, you have a second statement. What about the derivations of the space of convergent series? It's the same statement where you, of course, you require f to be convergent. And by the way, if you know d, how do you find f? You just evaluate d on a very particular series, which is t. And that's half of the solution of the proof of that fact. I mean, this is the only possible candidate. So if you want to prove this fact, you are left with proving that I take an arbitrary derivation, I subtract dt d over dt, and I should find the zero derivation. And this difference vanishes on t by definition, but it's a derivation. So it vanishes on t, it vanishes on t squared, on t cubed because of Leibniz rule. So it vanishes on all polynomials. But now you must prove that it vanishes everywhere. So that's an exercise for you. Well, there is an easy solution. Assume that it is continuous for the formal topology. I mean, the t-adic topology, topology of formal convergence. Then it's immediate. But you don't need to assume it. You need not assume any continuity. Automatically, any derivation is of that form. That's an exercise. We can speak about it tomorrow. I wouldn't say it's easy because it took me so much time to find this proof. So that's a fact. Now we restrict to a smaller space, large enough to capture all the convergent series. And now we have a huge family and they are all independent. They are free in a very strong sense. But the delta omegas are free in a very strong sense. They generate, I mean, when you have derivation, you can do commutators of derivation and you have new derivations. So you generate this way a Lie algebra. They generate a free Lie algebra of clearly of infinite dimension. because they generate a free Lie algebra of infinite dimension. And that's quite extraordinary, yes, because you will see, hopefully, that the definition is very analytic. We will use the Borel transform, we will go into the Borel plane, and where in that plane we will manipulate analytic functions of one variable. We will follow analytic continuation. So the mini-course has a very analytic flavor. It's about analytic continuation of holomorphic functions of one variable. So it's very analytic. And here, this is a very algebraic statement. I mean, as far as I know, the only freely algebras of infinite dimension, you find them in algebra as abstract constructions. So this is very concrete. These are operators of very specific algebras. So that's the goal, that's the aim. Now I start going into the details, definition of Borel, definition of Laplace, definition of R. That will be our first new object. Is it okay if I write here? You still read me?
Yeah, the camera will move.
I don't want to
Hello,
go that far. I mean, I'm too far from you now. I will lose contact.
No, the camera is on you. Yeah, sorry.
Can I ask something?
Oh, yeah.
That kernel of delta omega, the kernel of delta omega, does that only contain the convergent series, or is there more to it? Because you've written
that's
subset.
a good question. There is more. There is more. Good question. There is slightly more. So yes, they are meant to detect divergence, but a specific kind of divergence. There are non-convergent series which happen to be in the kernel. And that's not difficult to find. You will see it in the definition, but that's a good point to remember. So, well, before I mean, I like to give examples. So let's take a few examples. So this way, I fuel the suspense. So what are these resurgent series? How will we? But well, let me give you a few samples. The most famous resurgent series of all times is Euler series. Phi tilde, let me put nothing, okay, phi tilde, yes, of Z, of T. So I start with 0, but I shift, I put here n plus 1. So there is a factorial, so factorial divergence, of course, the radius of convergence is 0, factorially divergent. And well, it's called like that because there is a famous article by Euler in 1760 about, well, to be honest, he was interested in the specialization when t is 1. Can you give a meaning to that number? So can you renormalize that infinite series, which is not convergent in any reasonable way? Because when you specialize, the general term does not tend to 0. So no way. But at some point, he introduces the parameter t, and this is one way of assigning a meaning to the series. It's a nice article in Latin, De Seriebus Divergentibus. And well, for us, it's important because it's not, you see, it's not pathological. It's a natural object. And it's very natural because it is a solution to an ODE. Look at this ODE. You look for a function phi of t satisfying this. That's not a pathological ODE. But if you know the theory of linear analytic ODEs, so it's linear non-homogeneous. So there is a standard way of making it homogeneous if you insist. So you can think of the classification of linear ODEs. It has a singular point at the origin. So there is a singularity at the origin. meaning that everything here is regular and t is a polynomial. T squared is a polynomial, but it is in front of the highest derivative. That's forbidden. If you want to solve the Cauchy problem, you need d phi over dt equals something, and you specify the initial condition. So you can do that everywhere except at 0. Because when you make d phi over dt, you have 1 over t squared. So you cannot solve the Cauchy problem at the origin. So this is why something funny happened. If you were to look at formal solutions anywhere in the complex plane, you would find only convergent series. And once you have found one, in fact, well, it's linear non-homogeneous. So you know that the general solution, you obtain it from a particular solution by adding a solution to the linear equation. And the solutions to the linear equations, what are they? Exponential 1 over t. 1 exponential 1 over t. That is quite wild at the origin, you see. So the claim is this formal series, divergent, is a particular solution to that very simple ODE. So the question arises, what is the relation between the formal object and the analytic object, the analytic functions which do solve the equation? We cannot believe that there is not one way of extracting true analytic solutions from that formal series. So this will be Borel-Laplace. This will be one way to go from the formal to the analytic, but knowing that something strange happens at the origin. So that's our first example. So I mentioned Borel-Laplace, and the next claim is that this is a resurgent simple series. That's a claim. Okay. Second example. Second example. It's a very nice blackboard. Consider a function now, not a formal series. That is a function. I call it Z. And it's defined by an integral. And I call the variable, the integration variable phi, because I heard people speaking of field theory, and that would be field theory in dimension 0, I've been told, and you can look at the paper by Fauvet, Menuskeva if you wish. But that's a very simple example. So that's a function of t. It's an integral depending on the parameter. And the integration variable is phi. So where is it defined? You need, we're integrating from minus infinity to plus infinity. So clearly it's an exponential, no problem except at infinity. So this phi 4 dominates the decay provided real part of t is positive. So that's for real part of t positive. The half plane. Because if you move outside of that half plane, then you have to do something to keep. I mean, it doesn't mean the function does not exist outside this half plane. On the contrary, it just means that this writing of the function is valid only when real part of t is positive. But that's the trick in complex analysis. When you have one way of writing a function, you find another way, and you will discover that maybe, after all, the function exists elsewhere. And so do not believe that the vertical line has a special meaning for the function. It's not necessarily a singular thing. Well, at the origin, there is something singular happening. In fact, there is an asymptotic expansion. So I need to define that properly at some point. This symbol, there is an asymptotic expansion, well, in the very classical sense. Probably you know the meaning, and here is the series. So now there is a series. And there is a gamma here of 2n plus 1/2, but it is divided by factorial of n. And there is tn. So let me call this z tilde of t. So the tilde for me means formal. So, and you see that this is a formal series. Radius of convergence is 0 because gamma of 2n is something like the square of a factorial, and I divide by only one factorial. So the radius of convergence is 0, and this is the asymptotic expansion. I claim that as t tends to 0, when you truncate the series, you have better and better approximations of the function, which proves that the function has a problem at the origin. Because if the function were to be holomorphic at 0, its asymptotic expansion would coincide with its Taylor expansion, and it would be convergent. So this divergent series means that the function at the origin certainly has a problem, yes. But in a certain sense, this is the only problem it has. So that's the partition function, if you wish, but it's a toy model clearly for physics. It is resurgent. I mean, the series here is resurgent. And I think it's simple. I'm not sure. I don't remember. And you go from the function to the series this way. So I like this triangle. You have the series. Let's say, yes, the series on the top. And the function on the bottom. No, I usually put it like this, yes. So you go from one to the other by asymptotic expansion. So question, how do you go back? I mean, is there a sensible way of computing the function out of the series? Clearly, asymptotic expansion does not determine the function. Well, here we are. Well, think of my function exponential minus 1 over t. This is a function which has asymptotic expansion 0. So if I add it to z of t, I still have the same asymptotic expansion. So I cannot detect. I mean, now this is wild at the origin, yes, but on the negative side. On the positive side, this one is exponentially small. It is invisible. It is beyond all orders. So this exponentially small quantity, you do not detect it by standard asymptotic expansion theory. You need something more refined. You need maybe resurgence. So the inverse arrow still exists, though there is a way of choosing among all possible functions which have this asymptotic expansion. There is one better than the other, namely z of t, and the way, the systematic way will be Borel-Laplace. So what is Borel-Laplace? You will see in a minute, but it consists in two arrows, Borel and Laplace. So which means that and here I use this notation, z hat. Nothing to do with the z hat in Gukov's. Maybe some of you have heard about z hat. Sorry for the, so z hat of psi or zeta. I mean, it's good to change them. So here we will have something convergent with a finite radius of convergence, and we will do analytic continuation, and we will compute, I mean, Laplace transform. This requires the function to be defined on a half ray, or on a half line, starting from the origin. So this is what will happen. So this will be the general picture here already, here. And the next example, yes. The next example.
Can I ask a question?
Yes.
Yeah. So are you saying that there is something intrinsically better for one z of t among many? Or is it that the Borel-Laplace gives you this particular z of t?
Well, one way would be to say that I like Borel-Laplace, and I declare that by definition, the best one is the one provided by Borel-Laplace. But that would be cheating a little bit. But indeed, the one provided by Borel-Laplace has some qualities that distinguish it with respect to others. And be careful, it will come in a minute, but there are several ones provided by Borel-Laplace. I mean, this is something I should have said from the beginning. When you have a convergent series, you have only one sum. I mean, you take the ordinary sum, which is a bit dull in a sense. What you must think was when you have a resurgent series to which you can apply Borel-Laplace, it's much richer. You have several sums suddenly. You have several Borel-Laplace sums, and they differ by exponentially small quantities, and you want to analyze these exponentially small. So you have a whole world which unravels suddenly. So this is why, in a sense, divergent series are richer and more fun to study. So I'm not saying that there is only one obtained by Borel-Laplace summation, but I claim that those obtained by Borel-Laplace summation, including this one, have better qualities than a random. I mean, once you have one, you can add an exponentially small term and randomly, and that's not very good. So, well, that's part of the game, to define how better they are. I mean, but I'm sorry, at that point, I'm still very vague, so don't take my word for a formal, clean statement. So my third example, where is it? It's the famous Stirling series.
David, I think there's another question online.
Oh, yes.
Okay. Do you want to take it now? Or?
Sure.
Somdatta, do you want to ask a question?
So the question is, how do you get the asymptotic expansion in the first place without computing the real series? I mean, what is the way to get the asymptotic expansion?
How to prove that?
No, I'm saying that how do you arrive at the asymptotic expansion without first evaluating the original real series?
Well, in this particular case, the method I know is I am given this function and it's already an integral. So it's not too difficult to manipulate the integral. I mean, it's from minus infinity plus infinity, but it's even in phi. So I make it from 0 to infinity, and then I do some change of variable, and I insist on writing it as a Laplace transform. So this can be written as a Laplace transform by elementary manipulations. And once I have Z equal Laplace transform of something, then I have a general theorem which tells me, oh, good, take the Taylor expansion of that and apply inverse Borel transform, and you get automatically the asymptotic expansion. So I have a recipe. My recipe is, once I have Laplace transform, okay, the work is done by the general theorem, which I have not yet stated. Maybe tomorrow you will have the general theorem, which is very important then, as you realize.
You can also go past 12 o'clock. There's no hard thing at 12. You can take some extra time. There's no...
Oh, okay, thank you. Well, okay, yes, indeed, it will be frustrating. I mean, it would be too much suspense not to have anything about this Borel plane. Yes, you're right. Okay, the Stirling series is a very famous series. I mean, Stirling, that's not recent mathematics. It describes the asymptotics of the logarithm of Euler gamma function. So you know Euler gamma function, gamma of Z. So, well, it's a generalization of the factorial. I mean, if Z is integer, this is factorial of Z plus 1. So this gamma function, you meet it all the time. It's one of the most basic special functions. And you probably know that when you divide by square root of 2 pi, Z power Z minus 1/2 exponential minus Z, if I do that, the limit at plus infinity is 1. This is Stirling formula that we use all the time. I mean, it's when I told you the ratio here is roughly factorial, and this is what I had in mind because the dominant term here is Z power Z. I mean, up to geometric series, geometric terms. So, okay, this is Stirling formula. This guy tends to 1 when z tends to plus infinity. So let me take it for z real positive. Nothing fancy here. You know that the gamma function is defined in the whole complex plane as a meromorphic function, and it has simple poles at 0, -1, -2, etc. So that's a nice meromorphic function. So on the real line, positive side, no problem. At 0, there is a simple pole. Well, but you know that there is the functional equation. So this simple pole, I know it's a simple pole and I know the residuum. You know the functional equation. So this is how you extend it. And when you define the gamma function, one way to define it is by an integral. And when you look at the integral, you convince yourself that it's not only for z positive, it's for a real part of z positive, and the functional equation extends it meromorphically, because every time you iterate it, you introduce a pole at a negative integer. Good. Now I'm speaking of analysis. This guy tends to 1. So, and moreover, it's for z positive, it is positive, so it has a logarithm. So I can define a function mu of z by that formula, and that function mu of z tends to 0. And here is the statement: mu of z has an analytic expansion at infinity, which I call mu tilde, to be consistent with my system of notations. And this mu tilde is the famous Stirling series. So what is mu tilde? It's 1/12 z inverse minus 1/360 z minus 3 plus 1/1260 z minus 5 plus etc. Only odd terms. Only odd terms. But well, this function is not particularly odd. I mean, it has poles on the negative side and not on the positive, so it's. But the series is odd. That's a fact. And this formal series, again, there is this story of triangle mu of z, which is defined not only for z positive, it has a nice analytic extension, can be obtained by Laplace transform from the much awaited Borel transform of this guy. And so the claim is that this is again an example of simple resurgent function. And it's a rather elementary one. Let me try to be rigorous with my blackboard. Such a nice one. By the way, maybe you have a question here about the function itself. I mean, I have taken the logarithm. Why on earth do we take the logarithm? What about the function itself? It tends to 1? Well, it's not difficult to check that the exponential of a series which has an asymptotic expansion has an asymptotic expansion, which is the exponential. So yes, it's true that there is an asymptotic expansion, which happens to be nothing but the exponential of mu tilde. But the statement that this guy belongs to R simp is true, but not so easy. Actually, if you look on YouTube, there is a talk by Kontsevich maybe 10 years ago. He was dealing with resurgence. I mean, Kontsevich has been interested in resurgence as well as so many other things in the past years. And it was a certain number of years ago, and he was speaking about resurgence functions. And someone in the audience asked, after half an hour, can you please give us one example? And Maxim goes to the blackboard and says, okay, well, I have one example, but well, it would be this. but I don't know how to prove it is resurgent, and that's a problem with the theory. I mean, it should be the easiest example. Well, it was gamma of z plus 1/2. It was a mild variant of that. He was interested for a very precise reason in gamma of z plus 1/2, and he had no proof, so he was a bit frustrated at that time. So this is why I communicated with him later, because in Écalle's works, there is a statement that the exponential of a resurgent series is always resurgent. That was claimed by Écalle in 81. Well, the proof, I had written the proof because I couldn't find it in the literature. So I had worked on it and I was very happy with myself. So I was very pleased with myself. So I had written such a theorem and with all the details in the proof. So of course I decided I would send it to Maxime. But by the time I communicated with him, he had found direct proof, of course, because he's very smart. So he had found a direct proof for the exponential of the Stirling series. So that would be another lecture, by the way. But there is a beautiful formula for the Borel transform. So we need the Borel transform to understand all that. Borel transform, and then resurgent series. Okay, I will try to now to give you a few definitions after all these advertisements. Actually, it's better to work at infinity with negative powers. I prefer that. So I'm dealing with a formal series. Now it's a series in Z, non-positive powers of Z. And I write it in the form sum of A n Z minus n. So of course, and I mean, think that T is one of Z, and everything we have said about T is, yes?
Is there an easy example which does not belong in R sim, but it's still resurgent?
Yes, yes. It will be clear tomorrow. But well, since I have not given you the definitions, it's hard to give the example. But yes, the inclusion is strict. And you can find examples. Let me think. Yeah, by the way, I think you multiply it by 1 over Z, and it is still resurgent. I mean, it's stable. And I mean, you know that because I told you this is a subalgebra. So they are stable under multiplication. And 1 over Z is a convergent series. It's a polynomial. So if I take a resurgent series, I multiply it by a polynomial, it's still a resurgent series. But if the first one was simple, the second one may be not simple. So you will see why it's not difficult. Nothing. But simple ones, well, they are simpler for the exposition, for the definition of the alien operators. Well, this is a very simple definition. I define B like this. Well, I have a problem with the constant term. So what is this? I have A0, which is multiplied by a symbol, and then I have a nice series. So basically I divide by the factorials. But for some reason, I shift by 1 unit, and so the constant term is left over, and I put a delta here. Think that this is the Dirac mass at the origin. Dirac mass at the origin. Or think of it as a symbol. After all, so this will be this vector space. And this is my notation, yes. Okay, and what else? That's the definition, yes. And we are interested in those series whose Borel transform happens to be convergent in zeta. So we will be interested, so it's an exercise, I mean, absolutely immediate. What does it mean that the Borel transform is convergent? So what is Borel inverse of the convergent ones? I mean, of course, I don't care at all about the constant term. Like always, when you manipulate series, you are interested in the tail, not in the beginning of the series. So what is this? Well, after division by factorial, it will be bounded by a geometric series. So before division, it is bounded by, an is bounded by c m power n factorial n. I mean, or n minus 1 or n plus 1. I mean, it doesn't, you can vary m. If you're not insisting on having the optimal m, this is a good definition. So this is called one Gevrey. This is called a one Gevrey formal series when it satisfies this. This is exactly the condition so that the Borel transform will be convergent. And these guys will be very interesting. Let me go back left. Because we will define resurgent series now. So resurgent series.
So if the series is not convergent after Borel transform, can we do it once more? I mean, is it useful?
Say it again.
If suppose the series is not convergent even after Borel transform.
Oh yeah.
Can we repeat it once more?
Oh yes. And instead of doing that, you can divide by factorial 2n to start with, which would be like treating not z as the variable, but z square or z 1/2. I mean, yes. Imagine the series is 2 Gevrey. Imagine an is bounded by factorial of 2n. Then clearly you must do what you have said. Once you have divided by one factorial, it's still 1 Gevrey, so you must divide again. Or to start with, you divide by factorial 2n, which amounts to considering that the variable was not z, but z to the 1/2, so to speak. Because, well, for the moment, my n is integer, but n could be non-integer, could be half integer, for instance, and then it would make perfectly sense. So, yes, your question is very important. The theory covers not only 1 Gevrey series, but also 2 Gevrey or S Gevrey series, where S is any positive real number. You can have factorial n power s here. So in today and tomorrow, s is 1, but if you have different values of s, positive, then the trick is to change the variable. The resurgence variable will be a different one. And of course, you need to extend slightly the definitions, but there is a meaningful way of doing that. So again, for the sake of clarity and simplicity, I stick to integers n, and I define this now. Phi tilde is resurgent if, by definition, so let me write this symbol, I mean, by definition, if phi hat, first, phi hat is convergent. Well, there is always the Dirac part and the germ part. So the series part is convergent, has a positive. So now I have a germ at the origin in the zeta plane. In the zeta plane, I have a positive. I have a disk of convergence. And what I need is to study the analytic continuation of the germ part. And the phi hat has a nice analytic continuation. It has endless analytic continuation. But what does it mean? I need to tell you. So definition. So of course, when I say that, I neglect the Dirac part. So definition, if I had a convergent germ, I did just discard the Dirac term, has endless analytic continuation if and only if, by definition, if and only if you can follow its analytic continuation without ever encountering natural barriers what you encounter, you may encounter singular points, but only isolated singular points. And this analytic continuation, it's a parenthesis, and the analytic continuation may be multi-valued. May be multi-valued, that is authorized. So let me be more precise. What do I mean? Isolated singularities, never a natural barrier. I mean that you would like to follow the analytic continuation starting from this disk along a path. I mean, let's take Weierstrass's viewpoint about analytic continuation. Whenever you have a path, you try to follow, so you try to find analytic germs in small disks centered on points of the path. And if you can, then you say this path is a path of analytic continuation. Now, usually, not all paths are paths of analytic continuation. So usually you may have obstacles. Maybe after a while, hop, here you will not find analytic continuation because maybe here there is a pole or a branching point or logarithmic singularity or whatever. Or maybe here there is a natural boundary. I mean, there is sometimes the whole unit circle, sometimes the whole circle of convergence is a natural boundary, meaning that at any point here, if you draw a little disk as even a very small one, you cannot find analytic continuation. That's the definition of a singular point when you cannot locally find a way. So that's possible. So, but here it is forbidden to have a natural boundary, which would be something of, what is a natural boundary? Something non-isolated, a set of singular points which is non-isolated. That's what I mean. So then you take its closure and it's bad. But what we will have only singular points isolated. So maybe here there is a singular point, but it is isolated with meaning that you can circumvent it. So your path maybe was not good, but at the price of avoiding finitely many points, it is a path of analytic continuation. But then multi-valuedness is authorized. If you would have chosen a different way of circumventing here or there, you would have ended up with a different germ. So that's a more formal definition. So more precisely, so let me be very precise because this is a fundamental definition, a slightly complicated, but so let's say, in order to have finiteness, since we are speaking of things which should be isolated, if I stay in a compact, isolated implies finite. So let me fix in advance a bound for every L positive, and I promise my path will have length less than S, less than L. So I bound in advance the length of the path, and then there will be a subset, a finite set. Let me call it omega L, So a finite subset of C such that, and now it's a very clear definition, any path starting from the disk of convergence, the disk of convergence of phi hat is a path and avoiding omega L is a path of analytic continuation for phi hat. So I think that is a mathematical definition, rigorous enough. Well, if you want, okay. I forgot to write that the path has length less than L. I said it. Any path of length less than L. And I'm speaking of the length, so I suppose they are regular enough. So let's say Lipschitz. Regularity, no. Of course, if you take a crazy fractal path, I don't know. You never do that with analytic continuation. You usually stick to a continuous path. And Lipschitz is even better because you have the length, which is well defined. And that's clearly even smooth paths are sufficient for the purpose of complex analysis. So any Lipschitz path of length at most L, starting from the disk of convergence, avoiding these bad points. Maybe there are many of them, but you have fixed in advance. Your path has length less than L. It cannot go out of a big disk. And in this big disk, there are finitely many possible obstacles. But of course, when you increase the length of the path, you may have more and more singular points. And increasing the length doesn't mean the path goes at infinity. Maybe the path is going back. And maybe when it comes back, but it is longer, you discover new points which were not singular. Maybe this is in the disk of convergence, so it's not singular for the principal branch. But once I have wandered like that, maybe when I come back, it becomes singular. Maybe even the origin has become singular when I take too long a path. That's very possible. Maybe when you take all possible, the union of all these sets, maybe it's dense in the complex plane. That is not forbidden. But locally, it is finite. Locally, you have isolated singular points. You can circumvent them to the left or to the right. And it's not guaranteed that you find the same analytic functions. This is why I said the analytic continuation may be multi-valued, or it may be not. In fact, the easiest examples of resurgent series are those for which the Borel transform is single-valued, meromorphic. But after all, if it is algebraic, square root of a polynomial or something like that, or solution to a, then you know that there will be only finitely many obstacles in advance, but then there will be multi-valuedness for algebraic functions. And we are used to that problem. Well, you have to discuss which branch you are looking at. So with resurgence, you will be always looking at good ways of specifying which branch we are looking at. So we start with a principal branch, and then anything can happen. At these points, for the moment, any kind of singularity is possible. Simple singularities, that will be a reinforcement. I will impose that they have simple singularities. That's the point. What does it mean? I will tell you tomorrow. Maybe just to conclude, I tell you what are the Borel transforms of our three examples. If I may, in 5 minutes, it's okay. Well, maybe you are hungry, but anyway, the cafeteria doesn't open that.
Yeah, please go ahead. Yeah.
Okay, thank you. So we have defined the Borel transform by this recipe. I didn't tell you how I justify my recipe. Maybe I tell you in one word, and tomorrow I tell you more. What is it about zeta to the n minus 1 factorial, zeta to the n minus 1 divided by the factorial. This is Borel, but tomorrow comes Laplace. And what is the Laplace transform of that? That is z to the minus n. So that is the justification. I mean, it's not that, oh, my problem was too difficult, I had factorial divergence, so I decided I would divide by the factorials, and the teacher would not say anything. No, 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 we have a very good reason for doing that. It's very sensible. So what I'm saying here is the basics of Borel-Laplace summation, but resurgence is about this property, endless analytic continuation. So we will discuss the articulation tomorrow between summability, because what I'm saying here is that probably it would be wise to consider the Laplace transform of phi hat. And maybe this is a function, and this function, let me call it phi of z now. Maybe there is a good relation between this function and this series, but that requires that phi hat has analytic continuation along R plus. Well, maybe my function is resurgent, my series is resurgent, maybe phi hat is endlessly continuable, and indeed, for the principal branch, the real axis is free of singularity. But I need something more. I need growth at infinity to be such that the Laplace transform exists. I mean, for this to exist, you see, the Laplace kernel is decaying, and whenever real part of z is positive. Okay, all the time you have to think of growth, and so modulus of an exponential is modulus of an exponential is exponential of the real part. So here zeta is positive, modulus is given by real part of z times something going to infinity. So we would like phi hat to have at most exponential growth at infinity so that the Laplace kernel will beat it, and indeed the function is defined for real part of z large enough. And if that's the case, then that is Borel-Laplace summability. This is one, but not all. I mean, after all, why do I choose plus infinity? Why don't I choose a direction theta and try to follow the analytic continuation in another direction that would give me another function? And if between the real direction and the direction theta there is a singularity, probably there won't be the same function. So this is why I was saying you may have several Borel-Laplace sums out of one series, out of one Borel transform. Okay. This was just a justification to tell you that this division by factorial is not. And you remember I said Dirac at the origin. Well, what is the Laplace transform of Dirac at the origin? It is 1. I mean, in any measure theoretical sense, reasonable sense. So this is why I declared, well, think of it as Dirac mass, then you know what it means to integrate it, and you find 1. Which is good because 1 is the unit of our algebra, etc. Okay, so our examples, we had Euler series. So can we test this? Definition on Euler series? Yes, you can check at home, homework. It's very easy, this one. But where is it written? I don't want to write it wrong. I don't want to write it wrong. Yes. Euler, phi tilde. Remember phi tilde of t? Okay, I set z to be 1 over t, and then I apply my definition. It had no constant term. The Borel transform is the inverse of 1 plus zeta, the geometric series. So the geometric series is convergent. It has a meromorphic analytic continuation. The only single point is -1. So it is endlessly continuable. Yes. So this means that this one is resurgent, and the singularity is a simple pole, so probably this one is a simple resurgent series, but that's for tomorrow. Second example, we had this z tilde of t, the asymptotic expansion of the partition function in dimension 0. Well, I don't know what is the Borel transform, but what I know is that if I enlarge, if I extend the theory by authorizing half integers, what I told you before, so this is an extension. I mean, it was meant, I'm not changing the variable. It's not because I'm afraid of factorial 2n instead of factorial. It's not that, it's just that here it will be more convenient. So what is the the Borel transform of z power minus nu when nu is not an integer? Well, so there is always the shift. So you take the opposite exponent minus 1, like here, z minus n factorial n minus 1. And factorial n minus 1, this is gamma of nu. This was gamma of n, and now you use gamma of nu, so that works provided the real part of nu is positive. So this is the recipe I use now. And when I use this recipe, okay, again, z is 1 over t. So now we have z to the minus 3 halves, and then we have integer powers. So we get only half integer powers now. And all of them are, half integer positive. And when you do that, there is an improvement. This guy, you discover that there is a nice formula. So yes, it is convergent. Well, it is convergent with a mild singularity at the origin because I have introduced it here. So indeed, at the origin, there is a zeta 1/2. I mean, when you expand here, so this is square root of 1 plus 16 zeta. You expand it, usually, you take the principal branch of the square root if you wish, minus 1, and you get again the square root. So when you compute, you find that it starts with a constant times square root of zeta, and then, of course, you have only half integer powers. So if I factor out this square root, I'm left with something which is clearly convergent. I mean, this is clearly algebraic. Algebraic, this is not meromorphic, but this is still an example of endless analytic continuation. This is why I'm happy with this example. And where are the singularities? So you see that there is a singularity at the origin that I have introduced, but not difficult to handle because still I have a punctured disk of convergence in a certain sense. And certainly there is something happening at minus 1 over 16. So the only singularities are 0 and minus 1 over 16. And you can check that this algebraic function has several branches. You have 2 square roots here, but no other singular points. And finally, what about the Stirling series? You remember mu tilde, Stirling series. It was already given at infinity. It had no constant term, only negative integer as exponents. So what is the Borel transform? It is a nice meromorphic function. So let me get it right. So let's call it mu hat. And we will talk about it tomorrow, I think. Zeta to the minus 2, and it's zeta over 2 hyperbolic cotangent, zeta over 2 minus 1. Hyperbolic cotangent, that's a cosine, a hyperbolic cosine divided by a hyperbolic sine. So it has a singularity at the origin, but it's cancelled here. Well, but now I may have one, but no, because when you do the computation, you observe that there are cancellations. So this is as it should be. If it really is the Borel transform, you even know how it starts. It should start with 1/12. That would be the constant term. So indeed, you check that at the origin there is no negative power. There is a nice expansion, and clearly there is a meromorphic continuation. So clearly this is convergent, and you know where the singularities are. They are all possible singularities are, so not at the origin because it's cancelled somehow. But so at the origin we have a regular point, and then all possible singularities in this case are integers multiple of 2 pi I, and the hyperbolic sign vanishes on 2 pi I z, but it's divided by 2. So I get the hyperbolic sign vanishes on pi I z, but I have the 2, which gives me the set of singular points as 2 pi I z. So it's a nice meromorphic function. This is why it's so nice, and I can't resist. What about lambda? What about lambda? So lambda tilde starts with a 1. So okay, in the Borel transform, there will be a Dirac. And then exponential of a series. That was Maxime Kontsevich's question, which he has brilliantly solved in his own way. So the truth is that the Borel transform of lambda tilde is convergent at the origin. That is not the problem. That is easy to check. And it has analytic continuation in the complex plane, provided you avoid 2 pi I z. Here I made a mistake. 0 is not a singular point here, but it is a singular point for lambda hat. So this one has 2 pi I z as the set of singular points. So meaning that in the case of lambda, when you look at the Borel transform, you have the same disk of convergence. You can follow the analytic continuation provided you avoid integer multiples of 2 pi I, but you must, once you have left the disk of convergence, you'd better not come back to the origin. You will find a singularity there. So it's not meromorphic, it's highly multi-valued now. It's very multi-valued. So, but the singularities are still manageable. Locally, you see this, here locally you see a simple pole. In the case of lambda, locally you see a simple pole plus a logarithmic singularity, which is responsible for the multi-valuedness. So that is typical example of resurgent series. And by the way, just cannot resist again, here, you will want to take the Laplace transform in this direction. And well, believe me, you recover our function mu, the logarithm of gamma. And you can take any direction like this. So meaning that you can glue together the Laplace transform. So you get a very nice Borel-Laplace sum, which is indeed, you can prove it coincides with logarithm of gamma, with the appropriate stealing factor. What about these other directions? Why don't we look at them? What would we find if we were to look at those? I mean, this is a different function. I mean, by Laplace transform, I get one function here. I mean, believe me, it doesn't matter which theta you choose. But if you choose a theta prime here, you get something else in a different domain, by the way. So, which means that Stirling series has two Borel-Laplace sums. One, which is the function you expect, and another one, well, it would be interesting to discuss the difference between them. And if you do the exercise, maybe that will be, I don't know, the second lecture or the third lecture. So this is called the Stokes phenomenon, when you are comparing two different Borel-Laplace transform and you want to, I mean, clearly these singular points, they will be responsible for the difference between the Laplace transforms. Well, I'm going a bit fast here. I mean, we will have the slow motion version tomorrow. This is called, so clearly the singular points will play a role to analyze the ambiguity of summation, and that's very interesting, and that's handled through alien derivations. You remember I am supposed to define for you these mysterious derivations, these alien derivations. They are supposed to measure singularity in a way which will make those computations easy and tractable. Thank you for your attention.
Let's thank David for a very gentle introduction to resurgent analysis. Questions?
Yeah, so is there a characterization of resurgence series in terms of like, okay, these are power series solutions to differential equations with some kind of singularities?
No, not that way. The other way, yes, it's a theorem that when you start with an ODE of a certain kind, etc., the solutions happen to be resurgent. Well, it's a theorem. It depends. I mean, there are such theorems in Écalle's work, so you can prove such theorems. Well, you have to specify the category of equations, etc. But the converse cannot be true, I think. And I can't imagine a converse statement. And we will be dealing with differential equations, ODEs, like, I mean, Euler was satisfying, a very simple one. The Stirling series satisfies a very simple difference equation. Not a differential, but a difference equation. And that's interesting too. And in topological quantum field theory, they have underlying in the background, they have Q difference equations, and the resurgence variable would be something like logarithm of Q. So equations are important. And for me, that's the most natural source of resurgence. You have a problem, an equation of some kind, you find a formal solution, and you hope very much that it will be resurgent, because then you can play with these tools. So these are tools. Let's say it's a toolbox coming from Écalle to play with the formal series you encounter, maybe as solutions of equations. Well, sometimes you have no equation. Sometimes in physics, you have a formula, a generating series. And then that's more difficult, typically, because how will you analyze the Borel transform of something which has been generated by mysterious ways, by computing one by one mysterious invariants? Well, that's a good research topic, but it's not as elementary as what I'm discussing here.
Somadatta? Sorry, go ahead. Go ahead, Ashok.
Is there a similar result for integrals of the kind that you showed, like anharmonic oscillator? Would you have known that this should be resurgent from the beginning?
Sorry, say it again from the start.
I mean, is there a similar result for integrals, that integrals are always resurgent?
Integrals of what?
Of like anharmonic oscillator integral that you showed. Integral e to the minus half x squared plus lambda x to the 4. That was resurgent, right?
Ah, yes, yes. Very good point. I think it's fair to say yes, because precisely Kontsevich, for instance, has discussed examples of functions defined by such integrals, and he has a family of, I don't remember how he calls them, but he has discussed the resurgence phenomenon for a class of function, and there are two young people in IHES working on that kind of question. So the answer is essentially yes. So like period integrals with a parameter inside, it's very reasonable to hope that you get resurgent functions. Yes, absolutely.
Thank you.
And of course, if you think of Feynman integrals, etc., that's very meaningful for physics. But well, I'm not competent for that.
So is it possible to have some natural barriers still, or like in some directions, say?
Well, it's forbidden by my version of the theory. Actually, Écalle did something with certain kinds of natural barriers. I don't know exactly what. I mean, I'm more comfortable when there are no natural barriers at all, but that is not necessarily the end of the story. I know that there is a a book by Écalle in which he needed an extension of the theory, and he had a notion of, or he had coined a beautiful term for that. The functions were not endlessly continuable, but still they were, forgot the name. It's, I can show you the book. It's in French. It's about the Dulac conjecture, his proof of the Dulac problem. And he needed, he called that, so they are no longer resurgent functions, but they still are analyzable functions. So he has a theory of analyzable functions, which is an extension and which has room for such phenomena.
So
comment. Is there something? Yeah. Could you comment what exactly these natural barriers are in the Borel plane, right?
Yeah, in the Borel plane, yes.
If they are there at all. Now, what would they correspond for the original series? Like, can you comment on that? Like, what sort of a series should I have for phi tilde of z, so that I get these barriers, so to say?
So your question is about counterexamples. What are these which are forbidden?
Basically, what are these functions which do not have these endless analytic continuations, but they are still some sort of a convergent series in the Borel plane?
Well, there is a theorem which says that when you take a convergent series, let's say in the unit disk to normalize things, there is a theorem that generically convergent series with radius of convergence 1 has a natural boundary. So that's generic in a very huge sense. There is a beautiful work saying by Kahan, saying that in a very precise sense, if you have a random, if the coefficients are randomly distributed and bounded, say, so that you are sure that the radius of convergence is at least 1, then almost certainly the series has a natural boundary. I mean, the unit circle is, so that phenomenon is really extremely frequent in nature. I mean, in nature, precisely not in nature, in mathematics. But I mean, with our way of conceiving the definition of formal series, it's unavoidable. It's the rule. Now, the question is whether in natural problem, in problems of natural origin, I mean, series of natural origin, will you really find a natural boundary like that? So it's very easy to cook up example. I mean, take a lacunary series. I'm a dynamicist, so I take this series. It's easy to have a functional equation. When you replace zeta by zeta square, something happens. So this series satisfies an equation, a functional equation. And it's easy to use the functional equation and the fact that certainly it has a singular point at 1, because you cannot imagine that at 1 nothing happens. So because it has also a singular point at -1 and at all roots of unity of order, which is a power of 2. So this has a natural boundary. And I can say nothing relevant about its inverse Borel transform. I have no idea of what it would mean in the z variable. Here I'm in the zeta plane. So the phenomenon you are saying is very common. And in the z variable, what does it mean? Well, it means I cannot take Laplace transform, so I'm stuck. So it's, well, you can still have, as soon as the radius of convergence is positive, you can still use Laplace transform on a segment. And so what happens when you do that? Try to get a feeling. I mean, imagine you consider exponential from 0 to rho, where rho is before the boundary of the Laplace kernel. So imagine, well, in fact, it was possible, but I have truncated it. So the mistake I'm committing, I'm neglecting this. But clearly, this is exponentially small. I'm neglecting something. I mean, remember, z is going to infinity. And here, I'm neglecting something like that. I mean, real part of z. So there is a theory of approximate truncated Laplace transform, truncated Borel-Laplace summation. I mean, this So this is when I truncate. So this is the mistake I'm doing. So if you believe the Laplace transform has the right asymptotic expansion, then when I remove that, I do nothing to the asymptotic expansion. So this means that necessarily that was a very good Borel-Laplace truncated sum. So in the world of series whose Borel transform have a positive radius of convergence, at least rho, I can use that as a summation operator. I mean, truncated Laplace of the Borel transform. And I will have good things, yes. But one bad thing is that if my initial series was solution to an equation, the genuine Borel-Laplace gives an analytic solution, whereas the truncated Borel-Laplace version gives you an approximate solution, and the error will be exponentially small, which is good in certain situations. Actually, I've worked with that. I mean, in another life, I am doing real Hamiltonian systems, and there is the minicourse theorem, perturbation theory for Hamiltonian vector fields. And it's about exponentially small phenomena which happen. And I have one article with a friend of mine. We prove such a theorem. I mean, we prove a theorem, something like minicourse estimates, etc., using only Gevrey estimates. So using only a disk of convergence, but we know nothing out of the disk. And that is sufficient to do that and to get solutions with an exponentially small error. Well, but minicourse theorem is about stability in exponentially long time. And indeed, this exponentially small error means that you are safe only for a finite amount of time, but which happens to be exponentially large with respect to the small parameter. So I'm just saying that one can do very meaningful mathematics with that still. But the meaning of the natural boundary, it's hard for me to tell. No, can't tell you more.
Thank you. Yeah.
Well, thank you for the question.
I have a question. Can you hear me?
Yeah, we can hear you.
Yeah, so the way to evaluate that anharmonic oscillator partition function is to simply, if you want to consider the coefficient of the t to the n term, it's just the number of ways of creating pairs out of 5 to the 4n. I mean, if you have 4n fields, the number of ways of creating pairs out of them is just the coefficient of t to the n divided by n factorial because of the exponent, right? Because that's the physics way of evaluating it.
Maybe, but honestly, I don't follow you completely here. Well, what I can do, I can give you the file on which there was the reference, the paper by Fauvet, Menuskeva. They study a category, a family of examples, certainly containing that one. And probably they took care of giving the relation with field theory, and probably your question might find an answer in that paper. So I can make available my file, because honestly, I don't know how to answer you. I'm not proficient enough with field theory.
No, my question is, once you have the series and you evaluate the Borel transform or the resurgent series, what is the exact value that you get from doing this? I mean, can you evaluate, for instance, the energy eigenvalues of the anharmonic oscillator, for instance, using the Borel transform?
Oh, the eigenvalues of the anharmonic oscillator. This is what you said.
Yeah. Can you evaluate? I mean, for instance, normally you wouldn't be able to do it. What I'm trying to get at is whether there is any utility in doing this Borel transform.
No, but I mean, eigenvalue problems in quantum mechanics, you don't solve them by just one integral. I mean, maybe one integral will be the first term of an approximation process of some kind, but I mean, they are not integrable like that. I mean, that was the point in the VOROS article I mentioned at the beginning, 83, the quartic oscillator. So that's even simpler than that in a sense. It's a quartic oscillator. You're just phi4, and then but you consider the eigenvalue problem. So your potential is phi4 minus constant, and the constant is the energy parameter, and you expect that, I mean, for certain values of the parameter, something will happen. You will have an eigenfunction, but that's a complicated problem. You don't solve it by one integral. But that was the beginning of the WKB story. That problem is full of resurgence, yes. But I cannot tell you. In fact, it's still a research topic. Yeah.
Great. I think there's many questions, but since we're already way over time, we can have those discussions over lunch and over the duration of the mini course. So let's thank David again for a very nice first lecture.